Good morning, good afternoon, good evening, whichever is applicable to you. Welcome once again to our virtual lecture. Today, I want to start chapter 8, the quantum mechanical model of an atom. This is one of the models of the atom, which I believe you may have covered in introduction to chemistry. I will highlight three atom models. This is the latest model of an atom. We will look at how quantum mechanics is used in describing the quantum mechanical model of an atom. We described in chapter 1 or defined the word atom, the smallest indivisible part of matter. We will zoom in, look at the structure of the atom using the quantum mechanics. And without wasting my time, let's see, there will be part A and part B, unlike in the last 2-3 chapters, there were part A, part B, and part C, because such a section, there will be only part A and part B. This is the outline. This is what we will cover in chapter 8. The introduction, of course, for 8.1, 8.2, the nature of light atomic spectroscopy and models for of an atom. In the last part B, we look at section 8.4, 8.5, and 8.6. Please have a pen and a paper. There will be worked example I'll go through as usual. So what is quantum mechanics? In simple terms, quantum mechanics is the science that deals with the behavior of matter and light at subatomic scale. At subatomic scale, there's just an overview or just brief description of what quantum mechanics is. We will see how quantum mechanics has been used in describing or looking at the atom, looking at the electrons, where they reside, before we dive into electron configuration in chapter 9. What is a quantum object? When we say quantum object, it's an object or a particle that has both particle and wave properties. In other words, if an object has wave properties, which I know you know the properties of a wave, we will see later on. Like, you have seen the waves if you have been to depict that. There's the wavelength, the amplitude, the frequency, and so forth. We're gonna talk about that. And in particular, why we are highlighting this is in quantum mechanical model of an atom. Remember this, in quantum mechanical model of an atom, an electron, the objects we are just being, this is general, but in quantum mechanical model of an atom, an electron behaves as a particle and it behaves as a wave. We will see that down the line. So far, these are the models you should be familiar with. At the outset, there are 4 models of the atom. The first to propose the model of an atom based on the law of mass conservation. Remember, in the beginning, Antoine demonstrated that mass cannot be created or destroyed, and they were wondering why. There was some experimental observation. They could not understand why, when they weigh the mass of the reagent, mass of the product, there was no mass difference. Mass cannot be destroyed or created during a chemical reaction. This is set up the journey for the discovery of an atom, and the first person to propose reason behind the law of mass conservation is Paul. We call Paul's atomic model. In theory, he didn't perform any experiment, he didn't give, but there are 5 postulates which makes up Paul's atomic model. And J.J. Thomson, if you recall the plumb bonding model of an atom, it looked like this. J.J. Thomson model. of the atom. He proposed that there is homogeneous, homogeneous electron, negative, positive, negative, positive, negative, positive. We call Plum body, where the negatives are electrons, negative, these are electrons, and of course, positives are protons. We call it Plum-Body model of an atom. Recall the Ernest nuclear model. He bombarded the J.J. Thomson using the cold foil experiment. If you recall cold foil experiment, he bombarded the nucleus of coal with alpha particles which they were positive. It led to what we call the nuclear model. In other words, Rutherford model. When we say nucleus, he proposed that an atom is just simply an empty space with a dense region we call the nucleus. That's why nucleus, where we have protons and neutrons. By the way, I'm using positive for protons, and outside we have the electron. This is what Rutherford actually proposed in terms of the model of an atom. Where we are right now is the quantum mechanical model. This is the subject of chapter 8. I just wanted to highlight so that you can draw the parallel between all these models. You may think that we are still stuck at J.J. Thomson and say this is how the model looks like of an atom, or Ernest Rutherford could not explain the location of electron, but quantum mechanical model of the atom, this is the latest model of an atom, which we are going to look at in chapter 8. So in the beginning, it was believed that matter, until the beginning of the 20th century, it was believed that matter was deterministic. What do we mean by deterministic? That means you can predict the outcome of matter. For example, if I drop my car key, this is my car key. If I drop, it's just gonna fall on the table. It's just gonna, we can determine where it's going. If you, let's say a baseball player throw a ball, we can predict where it is. So until the 20th century, it was believed that matter was deterministic. We can predict where it is. Understand what this means? We can determine. Deterministic means we can determine, but it turns out that it's not the case, that we cannot determine the matter all the time, and in particular the electron in an atom. We cannot determine the location because they are revolving around the nucleus. There is no way we can determine the location. It's moving as a wave and in a constant motion. And the moment we know the location, that means it's no longer moving around the nucleus indeterminately. We will talk about that later on. These are failure scientists who worked over time, right, and discovered that subatomic particle, the present condition does not determine the future conditions. So if you look at all these names, Albert Einstein, you may have heard these, Bohr. Remember the Bohr model of an atom. De Broglie, we're going to talk about that, Planck's Hensberg uncertainty principle, and all these, all right, did experiment, and indeed they proved that there is indeterminacy in matter. So their work proved that matter is not deterministic. Therefore, it changed the course of the direction. I've defined the quantum mechanics before. Please get to know what this. It explained the foundation, which defined the quantum mechanics. What it is a branch of science. We deal with the behavior of matter and light at subatomic particles. It explains the periodic table, why it is. I know you know the periods, the rows, and why we have all these elements in the one group or one column. It's because of the quantum mechanics, which explain that the behavior of element in chemical bonding. We talk about the ionic bonding, covalent bonding, the sharing of electron. We're going to talk about the overlap in the next chapter, chapter 9, when we talk about the sharing of electron. Quantum mechanics explain the chemical bonding. It also provides the practical basis for lasers, computers, and many other countless applications, So let's look at the electron. When we talk about the behavior of the very small, the smallest you can think of, this is electron. An electron, a speck of dust, has so many electrons than the number of people who have ever lived on Earth. Just imagining the size of an electron, it is so small. It appears, apparently, the electrons determine the behavior of atoms. For example, group 1, they react the same way. They have one electron outside. We're going to talk about the valence electron down the line. But it's the electron which actually determines the behavior, the reactivity, the physical properties of atoms, of elements on the periodic table. Unfortunately, direct observation of electron in an atom is impossible. We cannot, because for it to look, we need to use light to look at where they are. And if you shine light on electrons, they behave differently, and it changes its behavior because they interact with light. That is the nature of behavior of electrons. So the quantum mechanical model now explains the manner in which electron exists and behave in an atom. Otherwise, it's just we use the quantum mechanics to explain the behavior. We cannot physically observe electron. Why? As I said from the previous slide, shining light on electron for us to see will change the behavior of an electron in an atom. So the only way we can tell the behavior of an electron in an atom of any element is using quantum mechanics to explain how electron exists, electron behave, where they reside in an atom. Remember the shells, energy level 1, energy level 2, energy level 3. We're going to talk about that. I'm just bringing to you something you may have learned about the energy level. That's quantum mechanics explaining the behavior of electrons in an atom. It also explains or help us understand predictive properties of atoms that are directly related to the behavior of electrons. So quantum mechanics, behavior of an atom, all right? Why, for example, sodium in group 1 is ferroreactive. It's because of the behavior of electrons in sodium, which behavior of electron in an atom of element sodium and many other elements on the periodic table. It also explains why some elements are metals or non-metal. It has to do with the what? With the electrons in an element, or even why some elements gain electrons or gain 1 electron, gain 2 electrons, lose 1 electron, lose 2 electrons, and so forth when forming ions. Quantum mechanics also explain why some elements are very reactive while others are inert. Group A, they are inert. Why? Because they have their outermost shell completely filled with electrons. That's quantum mechanics there. why could one are very reactive. We'll see other trend on the periodic table down the line, and this, the understanding why some of these are very reactive, quantum mechanics explain the behavior of those or the reactivity of those elements. Quantum mechanical model also explain why in other periodic patterns we see the properties of elements. For example, the recurring of physical or chemical properties on the periodic table. Remember, periodic pattern, periodicity. Quantum mechanical model explain those recurring patterns. We'll see later on periodic patterns in the upcoming chapter. So that's a little bit about intro on quantum mechanics. You can read more into text, make your own notes. I just want to shift to 8.2, the nature of light, the wave nature. Why do we need to study light? I thought we were talking about the electron. No, we need light in order to do what? In order to look at the electrons in an atom. Before we talk about the electrons, let's talk about the light, because we need light to do what? To look at the electrons. And light behaves as a wave. It has two properties. It behaves as a particle and as a wave. But before that, light is part of electromagnetic radiation. What is electromagnetic radiation? An electromagnetic radiation is composed of perpendicular oscillating waves, one for electric fields and one for magnetic field. So the oscillation here, wave, there is the wave, and then there is the electric field, and then there is the magnetic field. An electric, of course, electric field is a region where electrically charged particles experience some forces, positive, negative, all right? They experience some electric. And then magnetic field is a region where an object experience some magnetic forces when you place in the magnetic field. My iPad pencil is not magnetic. Therefore, if I place in magnetic field, it will not experience any force. So know these two types of field which constitute the electromagnetic radiation. Here is the speed of all electromagnetic radiation. They travel at a speed of 3.00 times 10 to positive 8 meters per second. Please remember this. This is the speed of light in a vacuum. We can say speed of light. It's just going to have that. And we designate using letter C. You will see in the equation, I will solve using the simple C for the speed of light. This is the speed of light, by the way. This is the speed of light. Remember that C stands for the speed of light. In some of the upcoming equation, I'll be using the constant C to mean the speed of light. Please remember to change the units to meters per second. Earlier on in section 1.6, right, in section 1.6 in chapter 1, we look at the dimensional analysis and the prefixes used. Remember 1 meter, so that when you are required to change 1 meter equals to 1 times 10 raised to 9 nanometers. 1 nanometer equals to 1 times 10 raised to negative 9 meters. Just to give you some of the conversion factors you may need to convert the speed from meters to nanometers and so forth. But remember, this is the speed of light in a vacuum, which we'll use later on. The oscillating electric and magnetic field, I'll not ask you, no one will ask you, but just oscillating up and down. This is up and down electric field, and then horizontal, this is the magnetic field, and this is the direction where the electromagnetic radiation is traveling. In this slide here, even though it's just seem simple, but there are one or two things I want you to take home from this slide. Somebody is seated up front here, assuming this is you here. If you see a lightning, or you may have noticed that you see the light before you hear the sound, it's because of the speed of sound is 340 meters per second compared to the speed of light, which is 3.0 times 10 to positive 8 meters per second. Okay. You see the light before you hear the sound. That is one point. The second point I want you to take home is, look at this. Light is traveling as a wave. You know a wave? There is a wavelength. We're going to talk about that. So when you see this zigzag or meandering, whichever way you want to call it, this is how light travel. All right. Anytime you see light, it's travel as a wave. We will come back to that later on. So characterizing wave, there is the amplitude, which we need to reproduce. If I were you, I'll have this. So the light is traveling like a wave. You need to know the distance between two crests is right here. The distance between two crests, let's say I have here this is called the amplitude, and here we call the wavelength, designated lambda, the wavelength. Right here, this is the wavelength of light, or electromagnetic wavelength. We call it wavelength. All right. So amplitude is the distance from the center all the way to the crest. This is called the amplitude. It's gonna have this so that you see amplitude. Let's see there. Gonna have that. So you should be able to define all these terms. Okay. Differentiate between wavelength using the Greek symbol lambda, and amplitude is a measure of light intensity. So the dim the light, that means this will be low. So this is a dim. Like here, I can say dim. It's not, it doesn't have high density. This could be bright because of the height of the amplitude. The higher it is, the more intense the light is. You have to know what amplitude signify in a wave. So we talk about characterizing the wave. There is the wavelength. Is a measure of the distance covered by the wave, distance from crest to crest, or even here. This also could be the wavelength, and this we designate using the Greek symbol lambda. I will also be using this symbol in the equation. Please know what it means. From one crest, see this crest is this distance right here, and here we call it the crest, or the distance between alternate nodes. Alternate nodes is the same thing for that. So far, we have defined the amplitude, the wavelength, and then there is the frequency, which you need to know. So far, this is the amplitude, this is the wavelength. But I just mentioned frequency. What is the frequency? Frequency is the number of, these are the number of complete waves passing a certain period over time. And we use hertz. This one hertz, H equals to per second. Units of frequency. It's not phi, but we call this Greek. This is Greek symbol nu, which represent frequency. This is the frequency. It designate frequency. I want you to go back to section 1.6 in chapter 1 again, so that when you are given the prefixes, you should know the numerical value you need to multiply. If this is the unit right here, unit of frequency. If this is the unit of frequency, suppose we have this. This means gigahertz. Giga means you multiply by 1 times 10 to positive 9, or megahertz. You may have heard about megahertz. Maybe kilohertz. What does that mean? These are just, expanding the unit of frequency. You need to know the factors you need to multiply by that, because in the problems you may be given and you want to just say, oh, I need to just plug it in there without changing the units. As we progress with the course, there's some concept you need to recall, or you are expected to know before you move on. So back to frequency, we use the symbol nu here. It's look like a V, but not. You see how I have here? Don't think that it is a V. All these now, they are interrelated. Frequency, wavelength, so that the speed of light, look at this, wavelength, their relationship with the speed of light in a vacuum of the frequency. That is the relationship between the two. And just like the density equation, given the two, you should be able to calculate the third one. Given two, you should be able to calculate the latter. So I can label this as relationship. Remember, this is always in meters per second. It will never change. It will never change. Frequency is hertz, which is per second as well. All right. That's what I wanted to highlight when we say relationship. This is where we are heading to. How do we use this equation? Remember, this is frequency, wavelength, or also this. If this is equation 1, we can also have equation 2 that C over lambda, this is equation 2, depending on what, but no one will ask you to calculate this times wavelength. But just, for general understanding, if you are to find, you rearrange this equation. And so far, we have looked at the relationship between frequency, wavelength, and the speed of light in a vacuum. And remember, C is 3.00 times 10 raised to 8 meters per second. I'll give you in a quiz, I'll give you in an exam, but your job is, how do you now, let's say you are completing Alex assignment online, you'll need to refer to the text, look at the numerical value for that, and you can't go wrong with that. Just general knowledge, what is, conceptual question, what is the vertical height of a wave called? The correct answer is B. It's pretty straightforward. So this is B, amplitude. Next time I may ask you to define the wavelength, I may ask you to define the frequency, know the definition of the 3 terms. Amplitude, wavelength, all right. This is a dim line. Remember the amplitude determine the intensity of the light. Because it has a shorter amplitude, or this is dim, this is bright. The wavelength of different lines, longer wavelength, maybe shorter wavelength, and we have here the frequency. One point I want to highlight on this slide is the color coding. You see, this is red, right? This is blue, yellow. This is somehow maybe blue, all right? And then there is a green here. It's not really by accident that the other is giving us a different wavelength, like this is like, no, there is a message which I want you to take home from here to make our life easier down the line. I will draw a wave, all right, a wave, and you will see if you look at how the wavelength is decreasing, moving from left to right on the whiteboard, it has to do with the color. So if I have here the wavelength right here, the wavelength, all right, it's decreasing as you move from right to left. Down the line, we're going to talk about the wavelength and the color coding. Remember, this is red, Richard, of yolk, crow, bananas in vein. This stands for red. This stands for orange. This stands for yellow. This stands for green. This stands for blue. This stands for indigo. This stands for violet. So these are the color coding which you need to remember. How do I know? ROEGB, some people call that, but I say Richard of York grows bananas in vain. Maybe the bananas were not doing well. This helps me in arranging the colors of the rainbow, you may call it, or the visible region of electromagnetic spectrum according to increase in wavelength. So here is longer wavelength, all right, longer wavelength, low energy. This region has low energy, longer wavelength, and low frequency, low frequency. On this side, there is high frequency, shorter wavelength, and high energy. We'll come back to this again, but I just wanted to show you so that when you look at this, red always have a longer wavelength. I'm using the colors of the rainbow. If you look at the blue, blue is somewhere here. Compared to maybe this is indigo or violet, you see it has a shorter wavelength. And then green is somewhere here. If you look at the green, it has longer wavelength compared to blue. You see the green, longer wavelength compared to the indigo, for example. Yeah, that's what I want you to make your own notes. Based on this, we will be coming back to that again. We'll be coming back to that again. So here is the the white light. If we use a prism, we can separate the white light into different colors, continuous, based on their wavelength. I just gave you this: red, orange, yellow, green, blue. You don't need to memorize this, but if there is a way you can reproduce this, it will help you. I say Richard or York cross bananas in vain. It will help you also to arrange the colors according to increase in wavelength. All right, this is decreasing in wavelength, going in this direction. Decreasing in wavelength, increasing in wavelength. You have to know which direction you can go. So here is the electromagnetic spectrum. It includes all other colors. Electromagnetic, all right? Electromagnetic spectrum includes the invisible colors of the electromagnetic, such as gamma rays, X-rays, radio waves. All right. Those are just few, and you need to learn how to arrange this according to increase. Look at this. Whatever we talk about Richard of York, look at this: Richard of York rose bananas in vain from red to violet. It's just part of this. Is the visible region of the electromagnetic spectrum from 400 to 700. Please, the numbers you see here is 700. Maybe even I can use this to show you that in this region is 750 nanometers to 400 nanometers. This is the wavelength. Outside this domain of 750 and, let's say going to 850 or 800 and coming down to 390 all the way down, you wouldn't be able to see with your naked eye, or we cannot see with our naked eye. So we call this the visible region. And when you look at this, you don't see, even though we are given in meters, this is in nanometers. This is in nanometers. So we cannot see the microwave. Every time you warm your food in the microwave, you don't see the wave. You don't see the radio waves. It travels through air. But if you have the receiver, you listen to whatever is going on. Likewise, for X-ray, you don't see the X-ray, even ultraviolet, UV light from the distant planet or stars is just travel through the airspace, unless there is something to block the light, but we cannot see. Even cameras, we cannot see. This is what I want you to remember, how to arrange them according to increase in the wavelength. Here we have been given in meters. We have been given in meters. This is just in nanometers. In nanometers, there's the cell for the cell phone, for the radio, for the TV, and for AM, right? Continuous spectrum, I know we looked at this. We will come back to continuous spectrum, but what is meant by this is there is a continuous, there is red. It's not like a line. We're going to compare a line spectrum versus continuous spectrum. Continuous means a red continues to might to yellow, yellow continues, and then it's might to blue, and then the violet is meant by continuous. If you spread that, see, it is continuous. Now, arrange the following conceptual question from electromagnetic spectrum. To complete electromagnetic spectrum, you are asked to arrange the given type of electromagnetic radiation in order of increasing the wavelength. You have to look at where they are on this slide here. And of course, it's going to be X-ray, visible, and then infrared. Remember, increasing wavelength. That means going from right to left on this right here, from right to left because the wavelength is increasing. And if I look at the gamma, X-ray, and infrared, gamma, X-ray, and infrared, gamma, X-ray, and infrared. So it's going to be gamma, X-ray, visible, and infrared. X-ray, visible, and infrared. So X-ray, visible region here, X-ray, visible region, and infrared according to increase in wavelength, according to increase in wavelength. So the correct answer is A for that. So you look at it. Let's see, conceptual on frequency, you'll be asked to calculate the wavelength or frequency, but this is conceptual. A source of electromagnetic radiation, this is the question, practice exercise 1. A source of electromagnetic radiation produces infrared light. Which of the following will be the wavelength? Infrared. It's not calculation. Let's underline the word infrared. And we are looking at the wavelength. Infrared is somewhere here. Look at the infrared. The wavelength is around 10 to negative 5. 10 to negative 5 is the wavelength for infrared. So which one of the following will be the wavelength? It cannot be 3 nanometers. No. It will not be centimeters. Cannot. The appropriate is micro. Remember in section 6. Not 6, but 1.6 in dimensional analysis, micro is 1 times 10 raised to negative 6 meters, which we know infrared is around that region. So the correct answer is A. There's another unit here which you need to know. What is this? This is, you read this as angstrom, which is the same as 1 times 10 raised to 8 centimeters, or 1 this is centimeters, 1 times 10 raised to negative 10 meters, 1 angstrom. It's the sum of the conversion factors you may see. 1 angstrom, there is a G here, equals 1 times 10 to negative 8 centimeters, or 1 times 10 to negative 10 meters, just to highlight what these units stand for. It stands for angstrom. Which of the following visible light has a longer wavelength? Unless you have mastered this diagram I gave you, it will be very difficult for you to draw a conclusion. It may not be necessary red and blue. I may give you a different, or somebody might give you a different color or different colors to compare either their energy or their wavelength. In this case, longer wavelength, red is here, that means longer wavelength, compared to blue here, which has a shorter wavelength. So the one with the longer wavelength is red. Next time, you may see orange and yellow, you may see indigo and violet, or even maybe the 3 combination for that, and you are asked to either arrange according to increase in wavelength, decrease in wavelength, or which one has the shorter wavelength, longer wavelength, and so forth. All right, let's see. Learning check. Calculate the frequency of green light. All right, green light emitted by a hydrogen atom with a wavelength of 486 nanometers, 486.1 nanometers. So at the outset, this is what we need to remember, that wavelength, we are calculating the frequency. First of all, wavelength is given by C over frequency, which means frequency, mu, is given by C over wavelength, where we are not given where C is 3.00 times 10 raised to times 10 raised to 8 meters per second. That one will not change. That one will not change. If you look at the value, somebody might just say 3.00 times 10 raised to negative, not negative, but positive 8 meters per second. And say, let me just plug in this 486.1 nanometers. How are you going to calculate the units? You need to forget about this. This is not the way you plug in. And I know most of you will forget to change the units. You learn, you should be well-rounded with the unit conversion. First, convert wavelength from nanometers to meters because of the speed of light. Look at this, because of the speed of light. Therefore, what we need to do is change 4.8 to what? 486.1 nanometers. You want to get rid of nanometers, which means 1 nanometer equals to 1 times 10 raised to negative 9 meters. How do I get this? Remember in chapter 1, all right? Remember in chapter 1, 1 nanometer equals 1 times 10 raised to negative 9. And 1 meter equals to 1 times 10 raised to 9 nanometer. You need to be able to do that. That's how I got this conversion factor here. Unit cancellation, this will go away, and what we'll have is 4.861 times 10 raised to negative, not 9, but negative 7, nanometers, negative 7 meters, sorry. This is meters, not nanometers. This is meters. So I've changed the wavelength to meters, from nanometers to meters. Therefore, we can now calculate the frequency, which is C over wavelength, which is equals to 3.00 times 10 raised to 8 meters per second over now 4.861 times 10 raised to negative 7 meters, so that the units will go away. And if you plug in your calculator, you should be able to get 6.17 times 10 raised to 14 hertz, or it's the same thing as 1.17 times 10 raised to 14 per second. Recall, hertz equals the same as per second, which is equals to, it's the same thing as hertz. So we have that, excuse me, I need to plug in my power. It's almost running out. All right, we good. So this is how you have the units for frequency. So what I've done is I've converted, and from here you can be asked to change to either gigahertz or hertz or kilohertz, megahertz, and so forth, depending on the question. Please look at page 351, problem 41 and 42 to practice more on using the relationship between the speed of light, the frequency and the wavelength of electromagnetic radiation. Let's move on to something else here, the particle nature of light. So far in part A, we have looked at the particle nature. We have looked at the particle nature. Let's just put here, I will label it this dual properties of light. One, wave nature, and then two, particle, which is now our second part we are going to look at as far as the properties of light. We have looked at the wave, the wavelength, the frequency, and so forth. That is one property of light. There is now the particle nature. That means it's like a particle. You know what a particle is. And before we understand that, how did we end up, or how did they figure it out that a light behaves as a particle? Light from your reading lamp travel as a particle. It's not like a wave the way we have covered in the part one. Even from the fluorescence, it's coming as a particle. So whatever we talked about as a wave, it's just like this, you see? So there are some particles. It's not like a continuous one. This is, I'm just showing you that light has some particle nature where dot represent a particle. How they ended up with that is there was some observation they could not explain. Somebody will explain the particle nature based on the observation. Remember, the law of mass conservation led to the development of an atom. They could not explain why mass before the reaction equals to the mass after the reaction. Likewise, before we look at the particle nature of light, there is what we call photoelectric effect. And what they noticed at that time they could not understand is when metal was shown, or when light is directed onto the metal surface, it was observed that many metals emit electrons. So this is what happens. So if this is the metal surface and this is the light now coming as a wave, when it strikes here, an electron is ejected in that direction. So remember, electrons are what? Electrons are negatively charged. So if this is the light coming as a wave, when it is shining like that, electrons emit. I mean, the metals emit electrons when light shines on their surface. This is called photoelectric effect. Classical physics or classic wave theory attribute this effect to the light energy being transferred onto the electron. So they assume that there is some energy from the light which is transferred onto the electron on the metal surface. This is the metal surface. Surface. I'm gonna have that, which is attributed to that. According to the theory, if the wavelength of light is measured, that, okay, this is what you are just assuming, that if the wavelength of light is measured, which means this wavelength right here is measured, the light wave intensity made brighter, more electron will be ejected. But this is not what the case. They were just theorizing, or the hypothesis was that if you decrease the intensity, it will take less time for the electron to be ejected. Or if you increase the intensity, electrons will be ejected fast. But the observation made contrary to that. Before we look at that, this is just what happened in photoelectric effect. Light source, electrons hitting the surface of a metal. It will be ejected and sent to some detections. It's just what happened. Light striking the metal surface, electrons are ejected. Remember, they were now saying that if we increase the intensity, more electrons will be ejected. But it turns out that it had nothing to do with the intensity. Experimental observation at that time indicated the following. It has to do with the minimum frequency needed, not the amplitude. It is the intensity that they must, the frequency. There is a threshold frequency where electrons will be ejected regardless of the intensity. We call this threshold frequency, the minimum frequency required for electrons to be ejected of the surface. High frequency light from a dim source causes electron emission without any lag time. So in other words, what they thought was for a dim light, there was going to be lag in emission of electrons, but it did not. Even dim light were ejecting electron as a bright light, but what is responsible for ejection is the minimum threshold. So if you look at here, this is the minimum threshold, either for the bright light or for the low intensity light. Both electrons, in both scenarios, electrons will be ejected. Electrons will be ejected. The person who explained this is Albert Einstein. Albert Einstein explained that or proposed that there is a minimum, or rather, light is released in packets. Let me go back to the previous slide here. And Einstein proposed that instead of a continuous wave you see here, this light is traveling in small packets, like a particle of light. So many particles traveling in a wavelength packet. And he called that packet of light photon. We just have here, photon, particle of light. And then photons, we call these particles of light. Photon is many. And then you have to understand quantum is one. Quanta, as in A, these are many or particles. So when you look quanta, it's one or photons. So photons, and that the energy of a photon of light is directly proportional to its frequency and inversely proportional to wavelength. Mathematically, energy of a photon is directly proportional to its frequency. It's the frequency and proportional to wavelength. We look at that mathematically. There is proportionality constant, which we will have it Planck's constant H. Here, this is called Planck's constant. You may need this in module 8. I'll give you in the exam 6.6 to 6 times 10 raised to negative 34 joules times seconds times seconds. So that now the energy of a photon is E equals to H C over frequency, or H V. Remember, this is frequency. Remember, C over lambda is the frequency. C over lambda, where C (3.0 times 10 raised to 8 meters per second. Therefore, wavelength must be in meters. Wavelength must be in meters. The lambda here must be in meters. This is how to calculate the energy of a photon. We're not going to go into details about the binding energy and so forth, but I want us to look at how to use the relationship between speed of light in a vacuum frequency to calculate the photon of, or I mean energy of a photon of light. How do you calculate one photon? Remember what I said, wavelength must be in meters. Calculate the energy of a photon of yellow light that has a wavelength of 589 nanometers. So at the outset, how are we going to do this? Our task is to calculate the energy. The wavelength is 589 nanometers. We're going to change this to what? To meters. So using the equation, frequency is the speed of light over the wavelength. And remember, this wavelength must be in nanometers, so that eventually we will plug in the equation H or equals to Planck's constant, energy equals to Planck's constant. And remember, the subscript here is energy of the photon. I want you to look at here that it is E, or energy of a photon. One photon, because sometimes you may be asked mole of photons. That means you have to multiply by that number. So here, this is the energy of a photon, which is equals to Planck's constant times the frequency, just to bring that to your attention that here is subscript photon. Plugging in that, this is the speed of light, right? You see how you have changed, or we have moved. This is changing the wavelength from nanometers to meters using the appropriate conversion factor. And this is the frequency, and plugging in the equation, okay? Energy of a photon of light is the Planck's constant, joules times second, times the frequency. We had to find the frequency using the relationship between the speed of light and the wavelength, and wavelength has to be in meters. So if you are asked by if you are asked to calculate the energy of 1 mole of, listen, 1 mole of photon of yellow light, then we multiply this value by the mole, all right, which is the Avogadro number. If you look at this, we use Avogadro number. We use that for Avogadro number. So let's see, having said that, having gone through the worked example, let's see another learning check problem, you are asked to find the what? Calculate the energy of orange light emitted per photon of neon sign with a frequency of 4.89 times 10 to 14. So E over photon, look at what I'm doing. Let me just minimize that, over photon. You have to use the subscript photon so that you don't make mistake, times the frequency. And remember, hertz, it was per second, it's the same thing. So if I plug in the Avogadro's, Planck's constant, 6.626 times 10 raised to negative 34, joules times second times the frequency, which is 4.89 times 10 to 14 per second. So that per second will go away with the second right there. Will remain with the units. This is 14. This will be 3.24 times 10 raised to negative 19 joules. Three significant figures, and this is the amount of energy per photon. This is per, I can even say per photon, for one photon. If it is for 1 mole of orange light, if it is 1 mole of orange light, you multiply by Avogadro number, which is 6.022 times 10 to positive 23, 1 mole of photon of light. Please look at problem number 43, 44, 45, and 47 on page 51 through 52. It's a good exercise. Some of these you have answers at the back of the book. It will help you in saving time to complete module 8 in ALEX. Module 8 in ALEX. Now, let's move on to 8.3, atomic spectroscopy and the Port's model of an atom. This is what he just proposed. Remember, he didn't design, he didn't give us a pictorial picture of the model of an atom. When you see here, it's Port's model of an atom and atomic spectroscopy. Before we look at the Port's model, spectroscopy here, let's divide these terms first. Spectroscopy is simply the study of interaction of light with matter. Light interact with matter is spectroscopy. We're gonna see how light is interacting with matter. Now, when atoms or molecules absorb energy, the energy is often released as light energy. You have seen just 4th of July, fireworks everywhere, different colors. You have seen neon light, etc. Let's focus on the fireworks. The reason why you see different colors during fireworks is because atoms absorb energy And once they absorb energy, they get excited. And once they get excited, they emit light of colors or photon of light with different wavelength. And you will see a screen or yellow or red, depending on the wavelength or photon of light. Photon of light. It has to do with the release of energy for that. All right. When the light pass through a prism, a particular wavelength is seen that is unique to that type of an atom or molecule. The pattern is called emission spectrum. Non-continuous can be used to identify the element. We can also see in flame test, you'll see later on illustration of a flame test you may have done in the lab, or you will do in the lab flame test where you just dip the flame wire in the test solution and then you ignite, you put it over the flame. Depending on the metal in your solution, you see characteristic color because also of what? Atoms absorb energy, and when they release that energy, you'll see it with different colors. Emission spectra to emit. Different elements emit light of different colors. This was observed in early 20th century that different elements of gases in an evacuated glass tube emitted when excited with electric current, they emit line spectra. We call this emission spectra for different molecules. The continuous versus line, this is continuous red, continuing to yellow, continuing to blue, and so forth. Continuous spectrum for white light, but for atoms, they have line spectrum. Only one line. You see the line spectrum from the word line spectrum for different elements. Take note of the numbers here stand for the nanometers. These two here, this is for two elements, hydrogen and neon. For white light, we see continuous, but for elements, we see line of discrete wavelength of SAR. There's a difference between continuous and what? Continuous and line spectrum. This is the line spectra for hydrogen, and Bohr used hydrogen to propose the model of atom. Remember, he's proposing only how the hydrogen atom look like. The line spectra for hydrogen has 4 lines. Let's count. This is red line, 1, 2, 3, 4. Around 654 red, around 480 or 490 for green. There is the violet or indigo. There are 4 lines for line spectra for hydrogen. Somebody by the name John Palmer derived a simple formula relating these lines so that when you plug in the equation, we call the Rayleigh-Spark equation of constant. Johannes, these are 2 people. He proposed or discovered a simple way of calculating this, but Johannes came up with a equation, a more advanced formula from John Palmer to calculate the wavelength of this. It really fits for only hydrogen. Remember, this is for hydrogen. So problems related to this equation, all right, related to this equation is only for hydrogen atoms. is for hydrogen atom. I know I have defined previously this is the wavelength, by the way. You know, this is the wavelength. Now, this heart rate is something new. We call it a Rydberg constant, or a in this equation. And it just, you need to remember, I'm going to give you this as well. 1.09 7 remember it is per meter. This is the units of the constant RH, rate per constant. You will be given, I'll give you, but if you are completing module 8 online or even attempting end of chapter problems, remember the rate per constant as a numerical value 1.09737 times 10 to positive 8, and then the reciprocal per meter. It could also be 1.09737 times 10 raised to 7. You may see something like that. It's the same thing. It's the same thing so long as you know how to work with that. So this, we can calculate the energy or rather the wavelength of a photon of light given off when an electron drops from higher energy to a lower energy. So this right here, let's just break down this. I've defined this. This is all the Rydberg constant, which you know now. You'll be given that. And then here, 1 over n squared minus 1 over n to square. Square that. Initial. So here is where the electron is dropping from and where it is dropping to. This is where it's starting from higher energy level to lower energy level. These are where N1 and N2 are energy level. They are energy level. Remember energy level 1, energy level 2, energy level 3, energy level 4, and so forth as you go. So if an electron absorbs light in a hydrogen atom to a higher energy level, maybe this is N2 and then this is N1, we can calculate the wavelength of that light. We can calculate the wavelength and it fits this line you see here with respect to red, with respect to green, and so forth. We call Rydberg constant, and you'll be given that you are asked to calculate. Paul now explain why this mathematical relationship works. This mathematical relationship fit is right here, here, and they didn't know anything. So Paul now is proposing why this is fitting. He proposing that when an electron is in here, interact with light, maybe I can just use this. This is what Paul is proposing. If this is the nucleus, right there, this is the and is proposing that if an electron is right here, this is E, an electron interact with light, let's say this is light right here, interact with this, it will be promoted to a higher energy level. This is excited, you say excited, it has more electrons. If it drops, emitted light. So let's explain this way, why this mathematical relationship is working in calculating the wavelength 650 and so forth, is proposing that if light interact with an electron in the ground state, we call this ground state, where it is starting originally, light, energy from the light, from the packets will be transferred into electron and it will be promoted, it will jump to a higher energy level. And when it relaxes, it will emit light of characteristic wavelength similar to what things. Remember, energy cannot be created or destroyed, we see as different. So that's what he proposed, Let's see, how do we calculate the energy? You see, this is highlighting electron in an hydrogen atom because this is only for hydrogen spectrum. So every time you see hydrogen with this equation, you need to remember that when an electron in an hydrogen moves from hydrogen atom moves from n is equals to 6 to n is equals to 1, a light of dash wavelength is emitted. So what do we need to do for here? We need to calculate the wavelength, which is RH 1 over n squared. You may call it final. 1 over n 2 squared. I may call it initial. So it's jumping from 2. So this will be (1.09)737 times 10 raised to 7 per meter into 1 over 1 square minus 1 over 36. 36 because it is 6 square. We are squaring. If you square 1, it's going to be 1. So this will be 1.09737 times 10 raised to 7. If I plug in values, this will be 1 minus 0.02778. To subtract that, 1.09737 times 10 raised to 7, and remember this is per meter, into 0.97222, which means 1 over, remember the left side of the equal sign is 1 over the wavelength. 10668, all right, 850.61, and this is per meter, still per meter. This is the same as saying this side is over 1, this side is over 1. We flip the equation so that we have here 1, it's going to be lambda, which is 1 over 1 equals to 1 over 1066850.6, all right, 1. If you flip over, that is the reciprocal of that, this will be lambda equals to, this is the wavelength, 1.9 0.37 times 10 raised to negative 8 meters. But this is not what we are looking for. Look at the question. You want to find out in nanometers. You want to find out in nanometers. So it turns out that, or you should know, you are expected by now to know 1 nanometer equals to 1 times 10 raised to negative 9 meters, or 1 meter equals to 1 times 10 raised to 9 meters. So we want to get rid of nanometers. I mean, like here, we want to get rid of that is the nanometers. I want to make sure for that. So we're gonna have it I want to have it my stylus is failing me a little bit, but we're gonna get that sorted out. Yeah. I don't want to save that. So that is the conversion factor we need. So this is what I wanted to show you, that how do we change this? You see this? We need to change to meters. So 9.37 times 10 raised to negative 8 meters. We want to get rid of our 1 meter here times, see this, 1 times 10 raised to 9 nanometers. Change that, the meter and the meter will go away. You want to cancel the meter and the meter to get the nanometers. All right. Which is 9.37 nanometers. It's kind of like, if you are not well-rounded with your dimensional analysis, you need to recall this. You will not be given, by the way. Let me just tell you the truth. By now, you should use the prefixes, nanometer, meters, all these. Why are we talking about nanometers? The expected that you have covered in the previous section, chapters, at the beginning of the semester, we look at the dimension. So this is the wavelength in nanometers. We have used the equation to calculate the wavelength, and then from there, we change the wavelength from meters here to nanometers there, from meters to nanometers. Please look at the problem number 75 on page 353. Now, light is emitted when gas atoms are excited via external energy such as electricity. If you look at this, what the point here is different elements, all right? Each element emits a characteristic color of light. This is helium, this is neon, this is argon, this is krypton, this is xenon, all right? Xenon on the periodic table. No Xe is xenon when excited with electricity. We will talk about the flame, 4th of July. You may have seen something similar to this. It's because electrons are excited. Somebody has to light the fireworks, right? That means they're introducing energy to the atoms, and then they get excited. And then the content of the firework they have different elements. Therefore, you see different colors because each element emit color with a characteristic or a characteristic color of light. You will see, or you may perform an experiment, we call it flame test experiment, identifying elements in a solution. Normally, there is an experiment at UNF. If you are attending UNF, if you took Chem Chem 1 lab, or if you are to take Chem Chem 1 lab, at some point you'll perform flame test on some solution where you dip the flame wire, put it on the Bunsen burner. You'll see different characteristics. You'll see a characteristic flame depending on the element. This is sodium, this is potassium, this is lithium. Brick red, there is greenish for barium, there is for calcium, strontium, and so forth. We used to identify the element using the already established fingerprints for flame test. So we just looked at how to calculate the wavelength of light for hydrogen emission spectrum, line spectrum for hydrogen. If you look at helium, there are more lines, 1, 2, 3, 4, 5, 6. 6, yet we know helium has 2 electrons. Hydrogen has 1 electron. It is a 1 electron system, 4 lines. The point, if you look at barium, we have so many lines. The point is, the more you have electrons, the more lines you will see for different elements. It's not only limited to helium, barium, and hydrogen. Different elements have their own line spectrum. Compared to white light, which has a continuous, it's not line, so continuous versus line. We talked about the line and emission spectra before. I've solved before the line spectral equation, how to determine the wavelength of light emitted by an electron in hydrogen atom, dropping from higher energy level to lower energy level. All right. So here are the problems with the nuclear model. Nuclear model is the one, cycle the nucleus, and then you have the energy level for that, but doesn't explain the structural changes when atoms gain or loses electron. The Ports developed a model for hydrogen. He did not propose model for multi-electron system. Multi-electron system are those with more than 1 electron, such as helium, lithium, beryllium, and so forth. He was only focusing on hydrogen to explain how the structure of an atom changes when it undergoes energy transition from lower to a higher energy level. And I've explained a little bit earlier on when I talked about the energy level 1, energy level 2, energy level 3, and so forth. We say that the energy of an atom is quantized, and that the amount of energy in an atom was related to electric position in an atom. Is related to electrons' position in an atom, which means it's quantized. What does that mean? I've used this before here. Let's see here. This is what I was talking about. This is energy level 1, and it's equals to 1, and it's equals to 2, and it's equals to 3, and it's equals to 4. We say that energy is quantized, means atom will have only one very specific amount of energy. Energy level 1, energy level 2, energy level 3, and so forth. It is quantized, it's not continuous. Electrons travel around, okay? Electrons travel in orbits that are fixed distant from the nucleus. So here is the nucleus. So we call this nucleus. We call nucleus and their fixed position. And remember, we have the neutrons and these are protons. There are protons in the nucleus. These are circular orbits. All right, orbits. Let's just draw the parallel between orbit. What is an orbit? This is right here. It is simply a circular. Around an object. Down the line, I want you to draw the parallel between orbit and orbital. We will talk about orbital later on. It sounds the same. You may think they're the same, but here is simply a region in an atom where there is high probability of finding an electron. It's a region of space where there is high probability of an electron. Just to compare the orbit here, which is a circular path where electrons travel around. They are stationary. And therefore, the energy of an electron was proportional to the distance of the orbit from the nucleus. In other words, if this is the model of hydrogen atom, an electron in energy level 3 will have a higher energy compared to an electron in energy level 1 that was mean, and they are stationary. They're just imaginary. It's just like the Earth revolving around the sun following its orbit. It's just an imaginary. It's not something you go there and then you find it. So these are the imaginary orbits where the electrons. Now, electrons emit radiation when they jump from an orbit with a higher energy down to. So if it is dropping down here, they will emit light of characteristic wavelength, and you will see as either red or blue, depending on the energy being emitted or depending on the photon of light being emitted. The emitted radiation was a photon. The distance between those also determine the energy of a photon and so forth. So that's how Paul explained, all right? He's explaining the Rayleigh equation, that why is it fitting? If you look at the color coding, this is low energy, it is closer. It's just right there, low energy, longer wavelength, by the way. Low energy, longer wavelength for red is intermediate, higher energy, shorter wavelength. Remember what is now explaining the lines. Is explaining the lines, explaining the calculation for hydrogen. And I cannot stress enough that Paul was working only with, I cannot stress enough that Paul was only working with hydrogen atom, not any other system. So when you look at this illustration, understand it is only hydrogen. Now there are assumptions or some take away from Planck's assumption to explain the phenomena he proposed. Energy level 1, energy level 2, transition, emitted. If energy is less, let's say here, let me show you what this means. Assuming that this is energy level 1, energy level 2, energy level 3. If an electron is dropping down, energy is given on. What this means is negative. Remember, exothermic, endothermic, what is given away is negative, what is absorbed is positive. So for absorption, it is positive, which means the electron is going to an excited state. And it's not only limited, by the way, to energy level 2. If it has sufficient energy, it can go to energy level 3, it can go to energy level 4, and so forth. But remember, it will come down again, meeting light of characteristic wavelength. So only orbits of certain radius corresponding to specific energies are permitted. That's what he took. He also proposed that an electron in a permitted orbit is in an allowed energy state. In other words, an electron cannot be just hanging in between energy level. It must have an allowed or permitted energy level for that to happen. Energy is emitted or absorbed by the electron only as an electron changes from energy level 1. So if changing of position or energy level here is associated with the energy, this energy is emitted or absorbed. This is absorption, this is emission. And we can use the same equation. This is the Planck constant. This is the frequency to calculate the change in energy, We talked about the ground state. Ground state is where it was originally level 1, level 2. We call this ground state. Electron in the lowest energy level, but it goes up. We talk about excited state. Any energy higher is called excited state. The energy difference between, energy difference between each energy level or between energy level is derived from this equation. This is where it is dropping from, this is where it is dropping to, and this is the constant, negative 2.18 times 10 to negative 18 joules. Therefore, joules, because we are calculating energy. This is not changing the internal energy. I know we talked about changing the internal energy, but when we have this equation, along with the energy level, this is the final means where the electron is relaxing to, where it is dropping to. This is where it is dropping from. Remember, you have to pay attention to the statement in question. So we're gonna have the relaxation, the absorption, the emission of light, all right? Absorption, emission of light, transition. What do the values mean using Bohr's model? It's just you have to understand the transition here has to do with absorption or emission, all right? If light is emitted, if light is absorbed from here, positive means energy is absorbed. Change in energy means negative means energy is released. And this change in energies from this equation, by the way, you're gonna use this equation, and this is a constant with a negative, so it's given out. The point here is the final and the initial energy state for that energy is released. There was some limitation as far as the Bohr's model of hydrogen atom. It's going to be specific to say that Bohr's model of hydrogen atom, it only works for hydrogen. I've been saying Bohr worked for hydrogen, it only works for hydrogen. It didn't work for helium, lithium, or any other element on the periodic table. The other thing Bohr could not explain is classical physics will result in an electrical falling into the nucleus and positively charged nucleus falling. Why? Because if we have proton in the nucleus, listen, look at this. If we have protons here which are positively charged, and we have electrons which are negatively charged, positive and negative to attract. And why is it not really falling into in here? Or simply assume it will not. It could not demonstrate, he assumed. So these are the limitation of Bohr's model. Let's assume that, he was asked, how do you explain why electron is not collapsing into the nucleus and annihilate or destroy the atom? He said, let's assume that will not happen. He could not explain for that. Well, he could not also explain the wave nature of electron. As it is turned out, if this is the nucleus, the electrons do not go in a circular motion. It just goes in there like wave, like wave. You see this? So electrons are traveling around the nucleus in a wave nature, which Bohr proposed that electrons just travel around in a circular manner. You could note this was the limitation of Bohr's model. But there were some important points which is applicable in quantum mechanical model of an atom, and this is the existence of discrete energy level. Yes, even today there is energy level 1, energy level 2, which he proposed. This is important in quantum mechanical model of an atom. We call these quantum numbers, N1, N2, N3. He proposed that. What is true also from Bohr's hydrogen model of an atom, that energy is involved in the transition from an electron moving from one level to another. It is true, even though he had some limitation. This is still true that the transition from any energy level to another energy level involve energy. That marks the end of part A. We will come back again in part B.